Good afternoon, everybody. I'm Aditya Krishna from University of Washington. And today I'll be presenting to you Lazy Receding Horizon A-Star. This work is in collaboration with Oren Salzman from Robotics Institute, Carnegie Mellon, and my advisor, Siddhartha Srinivasa from University of Washington. So this work was primarily motivated by robotic applications. Robots have permeated into various fields today: households, rehabilitation, surveillance, navigation. And much of the success that this field has seen can be attributed to decades of work from the planning community. As tasks become more complex and environments more cluttered, it is important to ensure that these robots spend lesser time in planning their paths while performing these tasks in cluttered environments. So that was the objective that drove our work. We wanted to reduce the planning time that these robots take in planning their paths. Planning for robots is generally done in configuration space. This is this continuous space that is defined by the states of the robot that explain the configuration of the robot. For instance, in this robotic manipulator arm, it might be the joint angles that define the configuration space. Since this space is continuous, we would like to, and planning in this space for optimal paths can be difficult, we discretize this space using a graph. So we sample points, build a graph, where each vertex denotes a configuration of the robot, and each edge denotes a traversal of the robot from one configuration to another via a straight line path in that space. So given this graph and given an environment like this cup, which translates to an oddly shaped obstacle in this space, we would like to find the optimal path. But note that since we are maintaining a graph and the environment is given to us, we do not a priori know which of these edges in the graph are collision-free. So the search algorithm that we employ needs to online determine which of the edges are free while searching for the optimal path. So since we have reduced the planning problem in a continuous space to a search over a graph, one natural thing to do is to employ A-star. So here you see the edges that are being highlighted are the ones that are being checked for collision. And the blue ones are the ones that are free, and the red ones are the ones in collision. A-star is great. A-star is optimal, correct, complete, and efficient with respect to the number of node expansions, but it doesn't necessarily explicitly reason about the number of edge evaluations or collision checks that it is performing. And that's a bit of a concern for roboticists because edge evaluations are expensive. And the way edge evaluations are done is each edge is considered to be a sequence of configurations. That is, so an edge is discretized, and the robot in simulation is placed at each of these configurations and checked against the geometries in the environment. If all these configurations are free, the edge is free. And if one of the configurations is in collision, then the edge is in collision. And it has been previously shown that edge evaluations is expensive in roadmap-based planners. This is from Chris Hauser's work, where he shows that edge evaluations is a dominant factor in the planning time. So most of it is edge evaluations. So maybe what we want to minimize is not necessarily the number of node expansions like A-star does, but we want to minimize the number of edge evaluations. And 2 years ago, right here at ICAPS 2016, Dylan and Srinivasa came up with and proposed Lazy SP, which does exactly that. Here you can see that it evaluates far fewer edges than does A-star. And we, in our work, show that Lazy SP is edge optimal. We close this theoretical gap that was left in Lazy SP's exposition. Meaning, in its class of algorithms, Lazy SP is the best you can do. It absolutely minimizes the number of edge evaluations. By the way, there are a few other interesting properties of Lazy SP. If you are interested, you should check out tomorrow's talk by one of my co-authors. So Lazy SP, what is laziness in search? This is a paradigm of search which reasons about the number of edge evaluations. And for this, it maintains an estimate for the cost of each edge in the graph. And for simplicity, we assume that this estimate is equal to the true cost of the edge if the edge is collision-free. And if the edge is in collision, the lazy estimate is still equal to the length of the edge if it were free, but the true cost would now be infinite because the edge is invalid. So with this assumption, let's see how Lazy SP works. It assumes initially that every edge in the graph is free. So it is optimistic under uncertainty. And using the lazy estimates, it finds the shortest path. Now the shortest path, since it has been found using the lazy estimates, it need not be valid. So the algorithm has to now validate this path by evaluating edges along this path. And when it finds out that a particular edge is in collision, it updates the graph by deleting this edge, for instance, and it finds the next shortest path. So in a way, it is going through the list of potential shortest paths and invalidating and rejecting each of them using edge evaluations, which is an expensive task. So it continues this process of finding the shortest paths and evaluating these edges along the shortest paths until it finds one potential shortest path that is completely collision-free. So it works great. It minimizes edge evaluations, which we thought we cared about the most. So what's the catch? And to understand that, let's take a look at how the search happens. So this is an instance when the first shortest path was being evaluated. The search tree here in light blue denotes the lazy search tree. So the search tree that was propagated using the lazy estimates. And I'm going to call that the lazy search tree. And note that when this search tree was built by assuming that all the edges in the graph are free. And when it finds out that an edge is in collision, it realizes that the algorithm has basically pushed the search tree all the way through till the goal when most of it is actually invalid. So it has wasted a lot of computational effort and time in pushing the search tree in probably a dense graph all the way through when most of it is actually invalid. So it's an obvious waste of time. So here it has two options. Lazy SP can either throw the entire search tree and start searching from scratch again, or it can be a little smart about it and repair this search tree that it has spent time on and built. So this is in line with lifelong planning A* from Sven and Lookahead. So we call this rewiring of the search tree. So it's a way to repair this search tree. And this can be expensive, especially in dense graphs. Chris Hauser actually shows that when laziness is employed, as planning time increases, the amount of time spent on graph operations increases. So the top two here, 60% of the time is being spent on graph operations and edge rewires than on evaluations. There has also been work that showed that as the size of your graph increases, the amount of time that you spend on graph operations increases substantially. So I would like to grab your attention to the rightmost bar here, which is the largest size of the graph, where 80% of the time is being spent on graph operations during search. So in a way, lazy SP shifts some of the blame for planning time from edge evaluations and collision checks to search and graph operations. So what we want to do is not explicitly just minimize the number of graph operations or edge evaluations, but we would like to strike a balance between these two costs that make up the planning time and reduce the planning time that the robots take to plan their path. So to set it up, on one end we have A*, lazy version of A*, and on the other end we have lazy SP. Lazy A* does absolutely no rewiring. As soon as it expands a node, it starts to evaluate. So there's no lazy search tree that it has to repair, which is a good thing. And on the, but it, in the process, does a lot more edge evaluations, which is bad. And on the other end, we have lazy SP, which absolutely minimizes edge evaluations, but in doing so, it can incur a cost in extensive rewiring and graph operations. This can be seen in the size of the search tree that is being built using the lazy estimates. Lazy A* does just one step look ahead. So it builds the search tree, one step, expands a node, and evaluates, while lazy SP pushes its search tree all the way to the goal. And we introduced the notion of look ahead to generalize this concept to capture how optimistic the algorithm is. On one end, you have lazy A*, which is extremely pessimistic. It does not trust its, I'm using that word a little loosely, but it does not believe in its lazy estimates at all, while lazy SP is completely optimistic. And in between, you have an entire spectrum of lazy algorithms, which might capture the best of both worlds. And we set this up under the framework of lazy receding horizon A*, or LRA*. So the key insight is by controlling how optimistic the algorithm is, how deep you want the search tree to propagate using the lazy estimates, we can strike a balance between the two costs that make up the planning time. And the way we define lookahead is the number of edges by which you want to push your search tree forward before you start evaluating edges to validate this search tree that you have built. Essentially, we want to control the size of this light blue blob that is being built as the search progresses. So let's see how it works. So along with the lazy estimates, you also give as input a look ahead. And so this is a zoomed in version. So you push your search tree until a depth which is defined by the look ahead. So here the look ahead is 4. So the search tree is only pushed by 4 edges at most. And once you've pushed your search tree, you look at the leaf nodes and you find the most promising node and you evaluate an edge towards that node. And every time we evaluate an edge and it is free, we ask the question if we have solved the problem, we have evaluated an edge to the goal, and if not, we push the search tree further. Because every time an evaluation is made, the lazy part of the tree is, the depth is decreased by 1. So we need to push our search tree to maintain this invariant that your lazy search tree is always of a particular depth. So we continue this process, and if there is a collision that is incurred, then you don't incur a lot of penalty because you have you're being cautious in expanding your search tree. Your search tree is basically bounded. The depth is bounded. So it's repaired, and this process continues until an edge to the goal is evaluated, at which point we have solved the problem and we get our shortest path. So we get the same shortest path as lazy SP or A star. So all the good properties of those algorithms are maintained. So to explain a little bit about the look ahead. So this is how the search at any point looks. There is a part of the tree that has been exactly evaluated. So the edges in this part of the tree have been evaluated. And there is a part of this tree that is lazy. And the depth of this lazy search tree is defined by the look ahead. And in a way, look ahead is trying to help the algorithm by gaining information from the graph. If the environment was completely free, all the lazy estimates are equal to the true costs. So the algorithm can is benefited by gaining as much information as possible. So larger the look ahead, more information it gets from the graph, and all this information is true, and the algorithm is benefited and minimizes edge evaluations. But if the environment is cluttered, if it tries to gain a lot of information, a lot of this information is false, and it has to incur penalty in performing graph operations and edge rewires. So we perform our experiments on 2, 4, and 7-dimensional systems. We run it on 10 different environments in each case, and in each environment 10 different graphs. So 100 experiments in total, and I would like to show you some of the consistent observations that we see. So look ahead, as look ahead increases, we show and we prove that as look ahead increases, the number of edge evaluations monotonically decreases. And this is in line with the fact that lazy SP is edge optimal, since lazy SP essentially has an infinite look ahead. We also empirically see that as the look ahead increases, the number of edge rewires increases. This we don't prove, but it is generally the case in cluttered environments and in dense graphs. And we also take a look at the planning time. And we note that consistently there exists an intermediate look ahead at which the planning time is at a minimum, so there is a dip in the planning time. And you can notice how it performs better than both lazy SP and lazy A star by balancing the two costs. So the blue is the edge evaluation time, the green is the rewire time, and the red shows the total planning time. We also perform our experiments on 7-dimensional robotic manipulator arm, where we look at a tabletop manipulation task where the robot has to move its arm to reach out for a shelf. while avoiding the obstacles on the table and the table itself. And here we notice a similar trend where LR A star with an optimal look ahead performs better than both lazy SP and lazy A star. And notice how when the look ahead is small, the dominant cost in the planning time is due to the edge evaluations, while running lazy SP and with a large look ahead, the dominant planning cost is from the graph operations. And to summarize, we note that by balancing both edge evaluations and graph operations, and neither of them just explicitly, we can reduce the planning time further, and we captured this entire spectrum of lazy algorithms defined by the look ahead under the framework of lazy receding horizon A star. This actually opens up a few interesting questions. What is this optimal look? What is the optimal look ahead? Can we learn it for different environments? And we actually see, notice, and show in our paper that similar environments have a look ahead in a small neighborhood. So given a class of environments and tasks, it should be, or would it be possible to learn the optimal look ahead and predict it? And a more interesting idea is, how do you are there alternate interpretations to the look ahead? So the way we interpreted it was the number of edges over which we want to push our lazy search tree. But if you interpreted it in terms of the belief that you had over these subpaths being collision-free, you could also think about varying your look ahead in different parts of your environment. Where it is cluttered, you want the algorithm to be equipped with more caution and only propagate its search tree by a limited depth. But when the belief shows that your environment, part of your environment is entirely free, you would want the look ahead to be as much as possible. So such interpretations of the look ahead can actually be very useful. That's about it. Thank you. And my poster presentation is on Friday, so if you are interested, you should come visit. Thanks.
So thank you for a very interesting presentation. It's not clear for me, is look ahead fixed during the search?
Yeah, the look ahead here, we fixed it, which is why I say I'm reducing the planning time and not minimizing the planning time. But ideally, you would want to vary the look ahead as the search progresses, which I think can be captured if you interpret the look ahead in a different way, such as the belief over an edge being in collision or not.
Thanks.
Yeah, really very interesting. I have an observation and a question. Well, maybe just a question, let's say. The look ahead, you say that the look ahead may vary depending on the application, and you named the environment, but I suppose it's relevant to think that the look ahead may be better, shorter, or longer depending on the type of motion that you're considering here. Perhaps if you were to use a robot that is more constrained in motion, you would need a shorter look ahead. Exactly. Whereas if you have you given this some thought?
Actually, so if I think a parallel would be if the state dimension increases to a very high number, then you can imagine how there is a lot of free space because you are planning in a very high dimensional space, but your collisions and your constraints might be in your task space, which is three-dimensional space. And in this case, we actually see that it might be better to have a larger look ahead because there's more free space relative to the number of constraints that the robot is acting within. That is an observation that we see.
It's very interesting. Yeah.
Okay, so you've shown in the graphs a couple of slides back the distribution of time as a function of the look ahead. So I think you scrolled past it somewhere here. Yeah, like this. Would it be possible to determine the look ahead dynamically by simply taking a look at the evaluation time of the last couple of iterations, for example?
Yeah. So in essence, what you're doing is you're propagating your information about the evaluations, right? You're saying
Yes.
my edges are not independent. The collision status of my edges is not independent, and the closer the edges are, the status of them is going to be similar. An edge next to an edge in collision might be in collision.
Yeah.
Yeah, and that I think is very much possible. And I think if you are maintaining a belief over your edge validities and interpret Lookahead in that way, I think that captures exactly what you're saying.
Okay.
Yeah.
Okay. Thanks.
Thanks.